All right, finally, we have enough information to look at the constraints that approach the learning. And I hope that as we go through it more and more, you will see that I'm adopting a similar approach with you guys. And before we start this, I want you to think about the way that I'm interacting with you right now. I'm encouraging you to ask questions or you to come to me. I'm trying to give you as less explicit or as little explicit information as possible. And I'm just waiting for you to start producing that coordinated, structured behavior. Yeah, that is your assessment 1, that is your assessment 2, that is your assessment 3. So please, as you see that we progress more through this lecture and you start seeing that I'm behaving towards you as I want you to behave towards your athletes, your clients, your students, etc., please know that it is whatever you are putting in, the energy and the effort you are putting in, that you are going to get out of it afterwards. Yeah, so I hope that becomes clear as we go. All right. So what will we do today? Finally, we're going to look at what a constraints-led approach to skill acquisition and motor learning is. Particularly, and some of you might remember this person, we're going to look at Newell's model of constraints. We're going to look specifically, in this case, at a volleyball serve, but we can use any example that we want. And finally, we're going to slowly look into some of the roles that practitioners could play. And next week is an extension of this week's lecture, where we will explain the rest of the constraints-led approach to learning. All right. So first of all, what is the background to the constraints-led approach? Well, we've all seen the traditional theories from the first lecture that we did together, and we all remember those traditional theories, and we all remember their inability to really explain how we can exhibit such coordinated behavior in so many different domains as humans. So we came up with the constraints-led approach to learning, where we said that coordinated behavior emerges under constraints that we can manipulate. And although we've only seen a very small portion, we can slowly start to understand that that constraints-led approach is potentially a much better overarching umbrella theory of motor learning and skill acquisition. And the good thing is, the constraints-led approach can basically be adopted by anyone. Whether you're a clinical practitioner, or a coach, or an education specialist, or a sports scientist, or nowadays in talent identification, for example, wherever you can see complex behavior as the final result, complex coordinated and structured behavior as a final result of a process, you can use the constraints-led approach. So hopefully that will help you in learning one theory that can be applied to different settings or different contexts. So basically, all these people, what they are trying to do is they are trying to have very coordinated, structured behavior emerge over time. That is basically what they do. And we're going to determine that as, or define that as skill acquisition. Now, when we know the constraints that act upon that behavior, we can do a few things with that. First of all, and that's quite clear, it helps us to structure their training sessions, helps us to structure their practice sessions. If we know which constraints we can manipulate that eventually help that behavior emerge, we can help develop particular practice sessions that would relate to that behavior as a final result. Also, it helps us to understand how much information, and I think that's augmented information. For those of you who don't know what augmented information is, augmented information is everything that someone can get from the task itself. For example, coaching feedback or instructional feedback. It helps us to understand how much of that feedback we should actually be giving. And some of the best peer instruction sessions, assessment 3 in your subject outline we had last year, were peer instruction sessions where those coaches said nothing at all, except for encouragements. Yeah? So that'll show you, or a constraints-led approach helps us to show how we can limit the amount of information that we are feeding to someone. Also, it helps us to understand how we can scale practice equipment. And something that you know is, for example, in junior basketball, the rings aren't as high as in senior basketball. And the reason for that is the constraints that approach to learning. When we manipulate that constraint, kids score more goals. When they score more goals, they feel more successful. And when they feel more successful, what do they do next week? They come back. And that's what matters. That's applying the constraints that approach to practice. And then finally, it's also important to understand the constraints that approach, to understand what we as practitioners can actually do. The power is with the practitioner now. All right. So how do those long-term changes occur over time? And this is where you have to use what we talked about as being the dynamical systems theory and what we talked about in the past week about informational and physical constraints. This is where you have to put it together. And basically what a constraints-led approach says, that a learner is a dynamical, complex system. Yeah? We talked about dynamical complex systems in week 1, 2, and 3. So a learner is a dynamical complex system that constantly searches for stable and functional states or attractive states. Yeah? So while someone, this basically what that means is while someone is practicing, and their body is a complex system, and they constantly look for the most economical way to perform a particular movement. And as we learn, we create different of those states, those temporary stable states, those attractive states. So while someone is learning, the whole process involves building an attractive state that results in particular coordinated behavior, practicing a little bit more, building a new attractive state that's even stronger, or reinforcing the first attractive state, etc. So as we learn, as we practice, we build attractive states, stable, energy efficient states of coordinated behavior. As we continue to learn, constraints are not just going to influence how we build those attractive states in a positive way. They could also break the stability of the system. And a good way to think about that is the constraint of increasing age. And as someone gets older and older, there are certain tasks that you can no longer execute. So constraints can also have a negative effect on learning. And then finally, what is our goal? Is we want learners to develop a whole repertoire of very stable, attractive states that relate specifically to their domain of expertise. And when they create those stable, attractive states, that is when they are very, very robust, very well protected against outside influences or environmental influences. So once you practice a lot and you build those attractive states, they become really, really difficult to break. An example of that is, for example, if you think of someone who's been swimming for years and years and years, and you try to change their technique. They've built an attractive state for a very particular technique of freestyle swimming. All of a sudden, you're going to say, oh no, in the phase, underneath the body, you've got to accentuate that S phase a lot more. And all of a sudden, they're going to say, all right, I'll try. But what's going to happen is they're going to expend more energy, etc. So they're going to try and break that stable, attractive state they've been working on for years. And that's obviously potentially negative. Right. So when we think of that repertoire, we call that the perceptual motor landscape. And so a repertoire of stable, attractive states. A good way to think about that is when you think about a gymnast. A gymnast doing a floor routine has a particular perceptual motor landscape that consists of different jumps, different rolls, different handstands, different dynamic balance exercises or drills, etc. So in other words, someone who practices that floor routine a lot is going to develop stable, attractive states for every single part of that floor routine. That's called a perceptual motor landscape. Oh, sorry, this is not someone riding a bike. That should have been a picture of someone riding a bike, but think about it similarly. Someone riding a bike, or a child learning how to ride a bike, is going to have to build attractive states for every single part of that riding a bike. how to press the pedals, how to hold the handlebars, how to steer at high speed, how to compress the brakes, etc. And all of those are going to build a perceptual motor landscape of riding a bike. Now, this is what a visual representation of that perceptual motor landscape could look like. And if you look here, all the way on top, that's where someone begins to learn. And let's think of someone as a tabula rasa, yeah, an empty slate. When they first start practicing, there's almost no attractor states that have developed. But as someone continues to practice, attractor states become more stable, deeper, and there are more of them. Yeah, so as someone practices, they build their perceptual motor landscape with more stable attractor states and more of them. But we also saw that that landscape is ever changing. It's an open system. Yeah, so as someone practices more, that perceptual landscape keeps changing over time. So in the constraints-led approach, we say that learning is adapting to changing constraints across different time scales related to development and experiences. So as we practice more, our perceptual motor landscape starts changing. Those grooves start becoming deeper. Those represent attractor states that are becoming increasingly more stable. Yeah? But sometimes one of those attractor states might disappear over time and another attractor state might build, etc. And all of you who've trained in your primary sport or in something else have experienced that. When you first start practicing, yeah, you get some sort of competence in a few parts of a particular skill. But as you practice more and more, those parts of those skills become better and better consolidated. And you become better at a specific part of a skill. For example, in a volleyball serve, you might become really good at serving the ball right above the net. Yeah? And you might be able to do it every single time. That's an attractor state that becomes more and more stable. It requires less energy from you, and it's going to be less manipulated by outside constraints. Because you can hit the ball over the net in practice, you can do it in a game, you can do it in any other environment. Yep. So the constraints-led approach says that learning or skill acquisition is basically building that perceptual motor landscape to be as stable as possible with as many really well-developed attractor states. So learners, in that case, learners are constantly looking for movement solutions that will help specify specific constraints. And the purpose of practice is to seek, explore, discover, and assemble those stable states of coordination. So that brings us to, for example, what you are doing as instructors or teachers or practitioners. What I'm trying to tell you is that with a constraints-led approach, you are going to look at skill acquisition entirely different. Because all of a sudden, skill acquisition does not become something that you instruct to someone else. No, it becomes you who creates the environment in which your students, your players, your clients can go and seek and explore the perceptual motor landscape and create their own attractor states. And that is something entirely different than what we've known about skill acquisition so far, because it takes the responsibility during practice away from the practitioners and it puts it in the camp of whoever is trying to learn. And the same thing that happens in the interaction between you and me. All right, let's think about how someone could use the constraints-led approach to talk about a task such as hitting a ball with a bat. So first of all, when someone for the very first time tries to hit that ball, what they're going to do is they are going to establish an approximate solution to a movement problem. In other words, they're going to say, all right, if the ball is very close to me, that's when I start swinging the bat, etc. And that's going to result in some sort of basic coordination pattern in the beginning of practice. But as someone practices more, that basic coordination pattern becomes a more refined solution to that movement problem. In other words, you're going to be able to exhibit behavior that is somewhat prone to variation. You cannot just hit a ball that's thrown directly at you, but maybe a ball with a little bit of spin, You'll still miss it from time to time, but you've got a pretty good basic idea of what a motor skill like that should look like. As you practice more and more, we get increased stability in that movement pattern. And so as you get different balls with different variations thrown at you, most of the time you'll be able to hit them. Then as you train more, you get the ability to adapt to new constraints. For example, you can't just do it in practice, but now all of a sudden you're able to hit a ball most of the time during a game. Okay? Finally, you're going to discard the less successful movement pattern. So in other words, as you start hitting more and more balls, you automatically start developing a certain strategy. When you hit the ball, you say, oh, that's a great technique. I hit the ball. It's been successful for me. I'm going to keep it, store it in the back of my mind, and I'm going to keep it so I can execute it later. But every time you are unsuccessful, you are going to discard. Yep. And then finally, that's going to lead to increased stability, etc. So we can see that this is a sort of cyclical behavior. And this does not require the input from a coach at all. Yeah? Do we all agree that all you really need to do to have this sort of behavior exhibit or sort of behavior emerge is just throw balls at someone as often as possible? So if we allow someone to seek and discover new movement solutions rather than telling them what to do, we're actually helping them. And that may be confusing to them in the beginning, but we're actually helping them build more stable attractive states. Okay? Let's see if you understand this. What happens if instead of throwing the balls at this particular player, baseball player, I go and I show him a video and I say, this is specifically how you should be hitting that ball. Do it exactly as I'm showing you. What is going to be the detrimental effect of something like that? Sorry? And why not? So what you said is they might not develop suitable movement patterns, but why not? Why is telling someone this is exactly how you should hit so much worse than saying, here's a load of balls, yeah, just hit them as you go?
Because the variables are very
All right, very good. And what are those variables? What did we term them? Constraints. All right. And what did we say? That coordinated behavior emerges under constraints. So if you tell someone this is exactly how you're going to hit that ball, what are they not going to do? Which part of that are they not going to do? Yes? Yes, exactly. They're not going to try and problem solve. Yeah, there is a particular movement problem, but you are already solving it for them. Yeah? Instead of giving them all the tools that they need for them to establish an approximate solution to that movement problem themselves, you're giving them the solution that might not necessarily apply to them. Yeah? So do we understand that as a coach, it is impossible to provide the exact perfect movement solution for every single individual under all the different constraints that might act upon this complex system? It is much better to let them self-discover, build attractive states, and then build on those attractive states later. Yeah? So I've given you a little bit of an insight. Let's go a little bit further. So skill acquisition, in that case, skill acquisition is an ongoing dynamic process that involves the search and the stabilization of those attractive states, those stable attractive states, across a perceptual motor landscape as each individual adapts to changing constraints. And that's a definition, but basically you just came up with that definition by yourself a minute ago. The reason why I put that picture in there is because I don't know if any of you used to play this game on the computer. Do you know that game? Yeah? So that fish can only eat smaller fish. And as you eat smaller fish, you have to navigate through that environment and you can't touch any bigger fish. You can touch smaller fish, but not bigger fish. So as you become bigger and bigger and bigger, you have to adapt to new constraints. Your own body size as a fish that changes over time. And it's similar to us in skill acquisition. As we develop different coordinated patterns over time, we have to change how we interact with the environment with those patterns. it's an ongoing process. And I had a really good question from one of you asking me whether the constraints that approach indicates that learning is a closed or open feedback loop. And this is a closed feedback loop. It's a constant interaction with the environment that feeds new interactions. That again feeds new interactions. Yeah, it's a closed feedback loop. All right. So then we come to Newell's model of learning, and this is the very first time that you'll see something concrete. How can we adapt the constraints that approach to someone learning a skill from the very beginning to when they are an expert? Okay? And Newell basically says there's 3 stages to learning. The first stage is where you assemble a basic coordination pattern. The second one is where you gain more control over that coordinative structure. And then finally, that's a skilled optimization of control. So that's what Newell says are the 3 stages. And we'll look at those 3 stages, both theoretically, and we'll look at examples from a volleyball serve. So first of all, when you assemble a basic coordination pattern, what you basically do is you get posed a particular problem. That problem consists of a lot of degrees of freedom, a complex system. As you practice a little bit in the beginning, you're going to develop an approximate solution to that movement problem involving a lot of degrees of freedom. And as we've seen, those are very complex problems. Okay? So what the learner does is they construct basic relationships between components of that dynamical systems, or that dynamical system that is learning a motor skill. So in other words, learners assemble different parts of the body, the trunk, the legs, etc. together, so it results in some sort of basic coordinated behavior. A good way to think about that is, how did we say in the lab, I don't know if you said it in the lab or in the lecture, but how are kids kicking a ball? You put a ball in front of a 2-year-old for the very first time, how are they going to kick it? What's typical of their behavior? It's very rigid. Yeah, so it's a swing from the hip, no swing in the knee, no flexion in the ankle, etc. So very rigid behavior. And we said, yep, that is exactly what they do. It is discovering an approximate solution to solving this movement problem. That rigid behavior, what is the benefit of having such rigid behavior? Controls the degrees of freedom, because there are less degrees of freedom. Yeah, just one single movement compared to multiple different segments coordinating or being coordinated at once. Yeah, so the movement problem is a lot easier. When the movement problem is a lot easier, it's much easier to find an approximate solution to that motor problem in the beginning. Let's think of a volleyball serve, and anyone who's played volleyball here, or many of us who haven't, if you would imagine picking up a ball now and hitting a volleyball, what a novice volleyball player does is they explore. They explore the perceptual motor landscape, and what that means is they're looking for the best approximate solution to the movement problem given the constraints. And the constraints in this case are individual constraints, such as, what is the length of my arm, how much muscular power do I have, what is my stature, because that's going to make a difference, etc. What is the strategic goal of this serve? Am I trying to score? Am I just trying to put the ball over the net so someone has difficulties receiving the ball, etc. So learners are going to explore a multitude of those different attractor states in the perceptual motor landscape. And how do you know whether someone is exploring the perceptual motor landscape when they're first learning a new skill? How do you think you can tell? Sorry? Mistakes, inconsistencies in performance. Okay? And the way that we explore the perceptual motor landscape is, if I hit the ball this way, this is what the result is. Is that result favorable to me? I'm going to repeat this behavior. And it's as simple as that. Yeah, so when we're exploring the perceptual motor landscape, we're looking for a sort of trial and error exploration. So as we said, A basic pattern might emerge over time. As you practice a little bit, a few hours, a basic pattern of a volleyball serve emerges over time. But that pattern is highly variable. Sometimes you hit the ball in the net, sometimes you might miss the ball, sometimes, I have that where I think this is going to be a great serve, and then I serve and it just goes boom, and over there. Yeah, so the spin you put on the ball might have been wrong, etc. Yeah, so we create a highly variable, but a somewhat stable pattern of coordination. And then gradually, as we practice more, a reasonably successful and stable pattern emerges over time. What is that pattern within the perceptual motor landscape? What does it look like when we go back to that slide with the visual depiction of the perceptual motor landscape? What does it look like? Yeah? This little bit in the perceptual motor landscape, the stable attractor state, yeah, that's what we're building now. So as we try and explore more different attractor states. So, as a player continues to practice from there, they slowly develop the ability to make small manipulations to that task. Putting a little bit of different spin, hitting it a bit further, maybe hitting it at one particular person in the opposition team who hardly ever is able to receive the ball, etc. Okay? And as they do that, as you add those small variations, instead of having that one dip in the perceptual motor landscape, all of a sudden, that stable dip starts getting another one next to it, and another one, and another one. Yeah, we're applying variation, we're building the perceptual motor landscape for a volleyball serve. All of a sudden, that also allows us to transfer positively from one of those attractive states to another one. Yeah, we would all assume that it's reasonable to expect that if someone is really good at serving, they might also be better at serving with a particular type of spin or adapting the serve to a particular spin. Yeah, so giving them that discovery approach to develop that very first attractor state is going to be beneficial in the long haul. So as someone learns, there's a continuous stabilization and destabilization of those attractor states. And learning is obviously highly dependent on which attractor states need to be developed. And obviously, that is facilitated by how much previous learning someone has done, how much experience, whether they've watched a video about how to serve a volleyball in advance. Okay? So basically, that is volleyball serve in the very first stage of Newell's model. Okay? The search and the exploration for new attractor states and slowly building the stability of some of those attractor states. All right. So once a reasonably successful solution to the movement problem has been found, people start to develop that stable coordination state. And what learners start to do is all of a sudden, that original degrees of freedom problem that was very difficult, as someone builds a better attractor state for that behavior, we slowly start releasing those degrees of freedom. Yeah? Remember we said beginners freeze the degrees of freedom, but as they progress through the stages of learning, they start unfreezing those degrees of freedom. Learners start looking for consistency, consistent behavior. This is what I said, trial and error. If instead of saying a successful serve has, a serve has been successful, I'm going to repeat it, you're going to say a serve, or this particular serve, when I do it, is successful 9 out of 10 times. That looks like a really good attractor state that I can develop further, etc. So, stable patterns emerge, for example, in volleyball, as long as the learner keeps exploring variations. All right, stage 2. So someone is reasonably good at serving a volleyball now, so they consistently get it over the net. There's a little bit of variation. They don't necessarily know where the ball is going to end up, but most of the time the ball goes over the net, and it's a successful volleyball serve. So what Newell says the next stage is gaining control over that coordinative pattern. So once that relationship between body parts has been established, we need to learn how to adapt to new environments. because there's no point in continuously being able to, or always being able to serve in a practice environment, but once you start going to games, you choke under pressure and you no longer perform. There's no point in that. Yeah? So as we progress through the stages of learning, Newell says, we're learning how to adapt to new constraints as they go. And again, there's going to be a huge role to be played for practice variability. And that emphasizes what we said the very first lecture, is that practice variability comes back in every single one of those models. It's one of the strongest concepts of motor learning or skill acquisition that we know. One of the certainties in trying to have someone acquire a skill is that someone needs practice variation. For example, someone might develop that practice variation or get more practice variation by not just serving from a standing position, but also from a jumping position. Not just serving with backspin, but also serving with topspin. And so there's different ways of applying that practice variation. Doing it at training, doing it during games. So Newell says in the second stage, that's all going to be about adaptability to new constraints. And that second stage of learning is characterized by subtle variations in the movement. So we're no longer, when we apply new constraints, we're no longer seeing that someone all of a sudden makes huge mistakes, and they're going to make small variations to the movement or to the motor skill. And that's going to be because that attractive state is being probed, it's being tested. All of a sudden, we've not talked about how to integrate action with perception as of yet, but all of a sudden Newell says we can't just execute that particular motor skill serving a volleyball, but we can integrate it with very online, live perceptual information. So in other words, we can adapt the way that we're going to hit a ball based on how the opposition formation is going to be. So we can use a real live online manipulation of that particular motor skill. So in this case, in volleyball, all of a sudden, someone is going to be able to adapt to how the opposition formation is going to be, and based on that, they can put topspin or backspin on the ball, they can do a floater serve, or they can do a jump serve, etc. Yeah, so we're going to develop in that second stage, develop a whole lot of adaptability to new constraints. For riding a bicycle, the same thing is going to happen. And the second stage of learning, someone is going to be able to not just ride their bike straight, but all of a sudden they can ride it between cones at high speed. They can integrate perceptual information with action. So that control stage, that second stage, is characterized by the reconfiguration of the motor system degrees of freedom. So that coordinative structures are more open to being reconstrained by environmental inputs. And so everything is going to be around developing that really strong bond between perception and action. And a particular part of that second stage is going to be something that's called metastability. And what metastability means is that as you practice in that second stage, you're going to build certain interactions between the environment and how you're going to control your motor skill that are going to be very temporary. Yeah, so in case of a serve, one might serve a volleyball, integrate that with particular environmental information, and only use it once. And after that, discard with it. And then as environmental information changes, the attractive states that you're going to use are going to change, but it's going to be temporary. And that's metastability. So parts of a system come together just long enough to form a functional movement goal, and after that, they get discarded with. And through exploring that metastability, a more advanced learner learns to cope with subtle variations in performance conditions. So it's very reasonable to assume that we can't just learn how to deal with every single constraint that we come across in our learning process. And that's where metastability comes in. It says that as you come across a particular type of constraint that requires one particular action from you, you do that for a little while, then forget about it. So learners in that second phase become increasingly more tuned to environmental information. And there's one study that showed that when someone is asked to serve a volleyball, without an actual volleyball being present, the movement pattern that they use to do so is entirely different than when a ball is present. And that shows us that when you couple perception and action, that is going to interfere with how you are going to build your coordinated behavior. Yeah, so it's going to interfere with which attractor stage you're going to use to exhibit coordinated behavior. So there's a strong information movement coupling or a strong perception action coupling in that phase. And those insights that we saw now on metastability, on how we exhibit more and more control over a particular motor skill are very useful, but they've got some issues as well, because the transition from the coordination to the control stage is not linear. So we know that from motor control and motor learning, that progressing through stages of learning is not a linear process. Someone might never go out of that first coordinated pattern stage, might never move into the control stage. Some people might skip one of those stages, etc. And so that whole process is not linear. And sometimes expert performers actually regress, they switch back. And the best way to think about that is under high environmental pressure, in this case, someone kicking a penalty in a very important phase of a game or a tournament. Kicking that penalty is hugely complex behavior. It's complex behavior that someone has practiced over and over and over again. And those players are incredibly good at dealing with the degrees of freedom that are, or that they are confronted with in this particular problem. But in some cases, they still miss that penalty. And by missing, I mean not the keeper catches the ball, but they actually do not even hit the target. And this is a particular example of how someone regresses in the stages of control. So they are sacrificing control under the emerging constraints in this particular environment, and instead of becoming less rigid, instead of becoming less rigid, they become more rigid, because all of a sudden this particular situation has more degrees of freedom that they can handle. They structure those individual components together. They sacrifice flexibility for more rigidity. And that sometimes ends in a miss. And that's why that's called choking under pressure. And then finally, the third stage of Newell's model is the skill optimization of control. And basically what that means is that all of a sudden, a learner has developed very coordinated behavior, and they are able to adapt it to almost every single environment possible. And they are doing it with increased energy efficiency and increased control. For example, increased energy efficiency, as someone runs more, the particular properties of their limbs even change. Yeah, so they allow us to run more economical because we get an exchange of energy or energy storage ability in our limbs. More smoothness and more fluidity in movement. And then finally, that final stage is a constant quest for looking for more stable and energy efficient attractor states. So what are some of the practical issues for learning? Well, we said before, a way to know whether someone has actually learned a particular skill or not is to do something called a retention test. And a retention test is 2 weeks or 3 weeks or 1 week after someone has stopped practicing, and we've done a post-test, we've looked at what the effect of practice was, we wait a little bit and we retest them again, and we see how much did they retain, how much did they remember of what we actually tried to learn them, or teach them. And in traditional theories, we say that the inability to retain is because we forget. We call that trace decay. That we forget what we were actually learning and therefore we perform less well. But the constraints-led approach says that the intrinsic dynamics or our ability to cope with constraints and ever-changing constraints decreases because the attractive state becomes less stable. In other words, an attractive state, a stable attractive state, is something you need to maintain over time. You need to keep practicing to keep that attractive state stable. So in other words, the more stable the attractor state, the longer the retention process. In other words, you are going to tell me after your skills project, when you do a retention test, 2 weeks after you've learned to ride a bicycle, you do it again and you can still ride a bicycle, you've still got a good time on your self-made, obstacle course that you've made. You're going to tell me, well, the reason I retained this is because I built such and such attractor states. Those attractive states emerged over time, and they are so stable, they are now part of my perceptual motor landscape. And that is what you're going to tell me. That is why you retain. Yes?
So you're saying in order to rank to more stable over time, you have to continually do it.
Yeah. You have to continually do it, and if possible, continuously do it with as much variation as possible. So you don't just build the main attractive state, but also the neighboring attractive state. So you can constantly transfer information between different attractive states. Because we will see, yeah? Sorry, not this slide, the next one, I'll come back to it. Yeah? So inability for retention might be a result of changing constraints. We said that before. Yeah? Constraints can actually be something negative. Your inability to maintain or be able to walk might be an effect of changing constraints as well. Then transfer. Yeah, so for those of you who know how to measure skill performance, you know what a transfer test is. For those of you who don't, a way to measure whether you have learned a skill is to transfer yourself into a new context that you've never seen before, that is very similar to that skill context from before, but not entirely the same. In other words, you might have practiced riding a bike on a self-made course, but you're going to test yourself on the road. It's a transfer test. And what the constraints-led approach says about transfer is it says transfer is definitely possible. And it is possible as long as attractive states are relatively close together, relatively similar. But when attractive states are relatively far apart in the perceptual motor landscape, it's possible that one attractive state pulls so hard, it's a negative transfer, one attractive state pulls so hard that it's difficult to maintain both attractive states at the same time. Think about it this way. You develop a particular technique for swimming in someone. And all of a sudden, after 10 years of swimming, you say, new evidence shows this is a lot better. And we start training that other attractive state. Then whichever attractive state you train the most, because they are so far apart, is going to be the one that becomes more stable, and automatically the other one is going to become less stable. And so that explains how transfer occurs between attractive states that are relatively close together in the perceptual motor landscape, but a lot more difficult when they are far apart. We called that last year, we called it the identical elements theory. And as two motor skills are very similar, positive transfer can occur between them. The more different they are, the less likely it is that positive transfer is going to occur. So for example, a good example of positive transfer is, for example, cricket bowling and javelin throwing. It is likely to assume that these two attractor states are close enough together to have some sort of transfer between one attractor state in one particular skill and another attractor state in another skill. I'm not saying that all cricket throwers are going to be the best javelin throwers, but they'll have some baggage, some experience, some attractor states that are already a little bit developed, that all you have to do is make them more and more stable and apply more variation. In other words, a javelin instead of a cricket ball. So, knowing all this, and we've got 5 minutes left, knowing all this, how would you change someone's old and preferred technique? Because what I'm telling you now is that when someone learns to practice, and they practice in a wrong way, and so they develop an attractive state that might not be the most economical, it is our job as practitioners, as coaches, etc. As clinical practitioners, for example, someone who has a wrong walking pattern and walks on the outside of their feet too much, it is our job to try and change that, right? But I just spent 50 minutes telling you that as someone builds a stable attractor state, those attractor states are very, very difficult to break. And the more stable they are, the more difficult they are to break. Yeah, so how would you change someone's technique like that? And there's a lot of research on changing old and preferred techniques because it is so difficult, but also because it is something that we're confronted with so often. People who have been doing a particular motor skill for so long in the wrong way, not the most economical way, because of certain individual constraints, for example, that it is difficult for them to change their movement behavior into something else. So how can we see that someone's technique is poor or someone's attractor states are poorly developed? Is someone's inability to adapt that technique to differing constraints, or an inefficient use of energy, someone who becomes really tired easily, or high prevalence of injury, which is the case if you constantly walk on the outside of your feet, or uneconomical movement patterns. So it is our role as practitioners, we have to understand that coordinated behavior self-emerges over time. There are very few individuals, and I'm not a gamer myself, but one of my PhD students, Matt, you've met Matt in the labs, he has a PhD project, looking at the expertise of gamers. And it is hugely interesting to me because these gamers have practiced, some of them, for 15,000 hours in the past 4 years, something that almost never happens in any other skill. And their expertise has self-emerged. They have no coaches. All they do is play online, and that's why I'm interested in that type of behavior. Yeah? That behavior emerges over time under constraints, and we have to understand that. Yeah? That's our role as practitioners is to facilitate how that behavior emerges over time. So one thing we can do is not interfere too much. Don't be too explicit. Use a hands-off rather than a hands-on approach. Develop the practice session beforehand, and then just let someone practice. Let them explore the perceptual motor landscape that they're going to use to execute a particular skill. Our role as movement practitioners is to apply movement variability, because we know that if we apply movement variability, the attractor state that we're trying to develop is going to become stronger and stronger and stronger. We can alter relevant tasks and environmental constraints to have certain behavior emerge. I'm not saying that everyone who wants to try and catch a ball should be put here and just a ball machine constantly shooting balls at them and they have to catch them. No, it is our task as practitioners to alter the size and the shape of that ball. For example, you saw informational constraints, we can manipulate them. We make the ball bigger and we make the ball filled with a lot of air or helium so it travels slower. Therefore, we're getting someone to catch a ball more often, more successfully. They catch a ball more often, more successfully with the right movement pattern. They're going to do what with that movement pattern? If it's successful, what are you going to do? Yeah, repeat it. And as you repeat it, what happens to the attractor state? It becomes more stable. All right, great. And that's when we add variation. So there is a role for the practitioner, but the role is different than the one you know. And hopefully you can see as you progress, that style of learning is much more modern than the old traditional models of constant hands-on approach. And this is what I should do, and this is what you should manipulate, and this is what you should be doing now. No, we create the environment. It's intelligent creation. And if you ever have a chance, a good way to look at your peer instruction session is something called the Teaching Games for Understanding method. And the Teaching Games for Understanding method is a method to teach kids about decision making in games. And I'll use that in a model training in week 8 and to show you how the Teaching Games for Understanding method works in the field. But it's good if you want to have a read, or if you're thinking about your own instruction session and you want to know how to start, the Teaching Games for Understanding method is a good one to look at. So this is something I want you to think about at home as a practitioner, knowing this. Okay? What if I would ask you, as a practitioner, for an assessment, you have to learn someone, you have to teach someone to learn to teach, you have to teach someone how to ride a bike. With what you know from a constraints-led approach now, how are you going to go, or how are you going to start that? Same thing with an experienced swimmer who requires a new technique, or a temporarily immobilized patient who used to be able to walk, i.e., who developed a really stable attractor state for walking, who can no longer walk now, but probably still has an attractor state somewhere. What are you going to do? How are you going to create those environments in which these people can learn optimally? And this straight away brings us to some thoughts about the skill learning process. And this shows us that skill learning is individual. And because you can imagine different types of individuals in each of those examples who will progress through those stages of learning in an entirely different way, will rely on an entirely different approach from you. And that's what makes the constraints-led approach so unique. It allows for the constant dynamical nature of learning, and it allows for us to apply this type of learning to different individuals at the same time. And that is also something you're going to have to do in your assessment 3. Some of the people you'll work with will learn really quickly. They'll want to be challenged a different way. Some of them will learn really slowly, and they'll want to be challenged in another way. Yeah, so I want you to start thinking about how you're going to implement that. There's more to this assessment than meets the eye. All right, so in summary, we've talked about the perceptual motor landscape. We've talked about how important variability is to build that perceptual motor landscape. We've talked about Newell's model of learning based on Bernstein's model of learning, which had 3 stages. And then finally, we've talked a little bit about how practitioners can use the constraints-led approach. Next week, practical examples on how different practitioners use that constraints-led approach. All right? Cool. I'll see you outside for questions because we have to leave here, or on Wednesday.